What are logic gates? A question that I've often been asked. So here is the first video on logic gates with more to follow, including Boolean algebra, which some of you may need for certain technical exams. Many of us have seen these symbols on some circuit diagrams, especially if you've been involved with industrial control systems, etc., or even just a simple electronic shower. We may know what they are called, but just what are they and how do they work? With automation taking over more and more functions, we need to have just a little understanding. We'll look at the very basics of logic circuits and logic gates, keeping it very simple and understandable. In the later video, we'll look at Boolean logic, one of the subjects of some technical exams and assessments, and there are some very easy questions at the end to test your understanding so far. A very brief history of the logic gate as we know it today. Logic circuits could be built on circuit boards with transistors, resistors, and so on, what we call discrete components, and I will show you some of those circuits. Back in the 1960s, they began to put these into plastic containers to make them durable and easy to handle, as well as protecting the components from damp conditions and so on. This was no-bit logic, and shown here is a 16-pin device, similar to today's integrated circuits, but about 4 inches in length, a real monster, and this was hardly more than a dozen years or so since William Shockley invented the first transistor. As silicon technology developed, it was possible to build smaller and smaller circuits and to reduce the size of the packaging to what we have today. The only reason that the modern integrated circuit is the size that it is because we as humans can't easily handle anything much smaller. Miniature devices are all machine mounted and oven soldered. Each device will have a pinout diagram showing all the inputs and outputs for that particular item. VCC is the positive voltage, usually between 5 and 15 volts, whatever is shown on the circuit diagram, and GND is 0 volts or the ground point. This device contains 4 dual input AND gates that can all work independently of each other. Logic gates work on binary inputs and outputs, ones and zeros. They return a logical result from the signals at their inputs. Logic circuits can be clocked so that they all work in synchronization. The ones and zeros are nothing more than the level of the voltage at the inputs and the outputs. 5 volts, for example, being a 1, 0 volts a 0. We will often talk about the signals being on for a 1 or off for a 0. Let's take a look at the logic gates now. What are the key features and what are the different functions? What are the main features of a logic gate drawing? In the examples shown here in green, there are 2 inputs on the left. Some gates can have 3 or 4 inputs or even more, but there is only ever 1 output per gate, and this is shown here as coming out on the right. Logic gates are normally, but not always, drawn as shown, inputs on the left, outputs on the right. The orange coloured gate shows the inputs and outputs in a common form of labelling. In this case, the inputs are labelled A and B, and the single output is labelled Q, although some favour the letter F for function, or some other appropriate lettering pattern will be followed, as long as it is understandable and makes sense. A truth table is shown bottom left. It shows us what the output signal will be based on what the inputs are, and we will look at truth tables soon. Some symbols, the blue symbol above, have an extra little circle on the output. This inverts the output signal so that a 1 becomes a 0 and vice versa, called a NOT function. These are the common logic gates, and by combining these we can build logic circuits and more complex decision-making functions. Should the vending machine put milk and sugar in your coffee, or just milk, or just sugar, or even nothing at all? The top left box shows the AND function, along with its complement, the NAND gate, with a little circle on the output. Whatever the AND gate does, the NAND gate does the opposite. The AND and NAND both have a flat shape on the input side and a semicircular shape on the output side. The NAND also has a small circle on the output side indicating the NOT function. The top right box shows the OR gate and the NOT OR gate. Look at the difference to the AND family. The OR has a curved input side and a pointed nose on the output side, with a circle on the NOR gate output. Bottom right is a special kind of OR gate called an XOR or exclusive OR, with its complement the XNOR or exclusive NOT OR gate. XOR and XNOR both have an extra curved bar on the input side, and the bottom left box shows two single input, single output gates, the buffer and the inverter, sometimes called the NOT gate, one with a circle, one without. There are many varieties of truth tables. By the end of this video, you will have the information that you need to recreate a truth table from scratch. It's very easy. Time to look at the gates and their truth tables in more detail. Starting with the AND gate on the left, as the word AND implies, the input A and the input B must both be in a 1 state, a positive signal, for the output to also be a 1. It needs A and B to be a positive signal. If any input is 0, the output will be 0. Now for the NAND gate on the right. Think of NAND as being not AND, not what the AND gate will do. So, if any input is 0, the output will be 1 this time. If both inputs are 1, the NAND gate outputs a 0. Look at the two truth tables, AND and NAND. The outputs are the opposite of each other. ORs and NORs now. 2 inputs and just 1 output again. With an OR gate, if any or both inputs are 1, the output will be 1. The NOR gate or not OR gate is the opposite to OR. If either or both inputs are at a 1 level, then the output is at 0. Otherwise, it is a 1. Now we have a special kind of OR gate, the XOR and XNOR. The XOR means exclusively OR. The output Q will be at 1 if and only if just one of the inputs is at a 1. If both inputs are at 1, then the output will be 0. It's exclusively a 1 if and only if the two inputs are different. Think of it this way. Do you want tea or coffee in your mug? You can't have both. It won't taste nice. And with the XNOR or exclusive NOT OR, the output is the opposite of the XOR. If one and only one input is at a 1, then the output is a 0. Take a look at the truth tables. And lastly, the buffer and the NOT gate. They have only 1 input and 1 output. Let's do the NOT gate or inverter first. Whatever the single input is, the output is the opposite. 1 in, 0 out. 0 in, 1 out. Easy. Now the buffer gate. 1 on the input gives 1 on the output. 0 on the input is a 0 on the output. What goes in comes out. But why? What's the point? A couple of reasons. We might want to clean up the edges of the signal before further processing, especially where the circuits are in an electrically noisy environment with lots of electrical interference. Or it may be a timing issue. Lots of circuits are clocked. The signals are read at predefined intervals regulated by a clock signal running at many megahertz. If a signal is likely to run ahead of the clock signal, it can be slowed down by passing it through a buffer. The extra work of going through a buffer will slow the signal enough, hopefully, to bring it back into line with the clock. Let's now look at a transistor logic gate, the simple buffer gate, starting with the input signal in an off state, so a 0 signal. We should expect the output, a light emitting diode in this case, to be off too. We are using an NPN transistor, and I've shown the 3 wires of the transistor in the red box. The collector is connected to the more positive part and the emitter to the more negative, or ground. In the off state, with the switch open, the transistor will have a very high resistance and no current will flow. No current will flow through the LED and the LED will be off. So, switch open, the output LED is off, 0 in, 0 out. If a positive signal is applied to the base by closing the switch, the transistor will switch on and begin conducting current. It will have a low resistance when on, and current will flow through the resistor, through the LED, and through the now low resistance transistor. This current flow will cause the output LED to switch on to illuminate. If the switch is closed, there's a voltage on the transistor base. Current flows and the LED illuminates. A signal in, a signal out. An OR gate is next. Let's get a little more into this and have 2 inputs and 1 output. 2 switches now, which are input A and input B. We start with both switches open, so input A is 0 and input B is also 0. To get an output, in other words, for the LED to light up, current must flow through the resistor and LED. But it can't. Both transistors are turned off, and with a high resistance on each, current flow is inhibited. This is equivalent to the first line of the truth table on the left. Input A equals 0, input B equals 0, so output Q is also 0. Now we close switch A and 5 volts appears on the base of transistor A. The transistor turns on and current begins to flow from the 5 volt rail through the resistor, through the LED and through the transistor. The output LED turns on. This is row 2 of the truth table. A equals 1, B equals 0, Q equals 1. Now we open switch A and close switch B, and 5 volts appears on the base of transistor B. Transistor B turns on and current flows from the 5 volts through the resistor, through the LED and through transistor B, and the LED turns on. This is row 3 of the truth table. A equals 0, B equals 1, Q equals 1. Now we can close both switches. Now both transistors have a 5 volt signal and both transistors turn on. Transistors A and B both conduct current and the output LED illuminates. This is row 4 of the truth table. A equals 1, B equals 1, Q equals 1. How would this work with AND and NAND gates? Let's compare them side by side and see the differences in operation. Remember what we said a little earlier about AND and NAND gates, the NOT AND gate. The outputs are the opposite of each other, and we have shown the 2 logic gates again here as a reminder, along with their truth tables. The AND gate will always appear on the left side of the slide and the NAND gate on the right. We have our switches A and B, both starting in the open or 0 position. First of all, notice the different positions of the LED in the 2 gates. In the AND gate, the transistors are in series with each other and the LED is in series with the transistors. The output LED is off because there is no current flow through the transistors. We have A equals 0, B equals 0, Q equals 0. In the NAND gate on the right, the transistors are in series with each other again, but now the LED is in parallel with both transistors. Because of this arrangement, with the LED in parallel, current can bypass the high resistance of the transistors and flow through the LED. The output LED illuminates, and we have A equals 0, B equals 0, Q equals 1, exactly what the Nand truth table predicted. Now close switch A on both of the circuits. What happens? Nothing, basically. Transistor A on both circuits has a 5V signal on its base, but cannot conduct current as it's being restricted by the second transistor. So we have, for the AND gate, A equals 1, B equals 0, Q equals 0, which means that the AND gate output remains off. For the NAND gate, both transistors maintain a high resistance and current continues to divert through and illuminate the output LED, a 1 signal. The NAND gate is A equals 1, B equals 0, Q equals 1. Now open the A switches and close the B switches. Again, there is no change in the outputs for the same reasons. Current cannot flow through the transistors. The AND gate is A equals 0, B equals 1, and Q equals 0, whilst the NAND gate is A equals 0, B equals 1, and Q equals 1. What happens if we close both switches on both gates? For the AND gate on the left, both transistors now turn on, creating a lower resistance path for current to flow. The current can now flow from the 5V rail through the resistor, the LED, and both transistors. This current now illuminates the LED, and we have a positive output, a 1 signal. A equals 1, B equals 1, and Q equals 1, as per the AND truth table. The NAND gate also has both transistors turned on. This creates a low resistance path to ground. The current that was flowing through the LED now sees a much lower resistance available and diverts away from the light emitting diode and through the transistors. Robbed of sufficient current to remain illuminated, the LED goes out, a 0 signal. What do we have for the NAND gate? A equals 1, B equals 1, Q equals 0. The opposite of the AND gate. Compare the truth tables. A little test or two now. Let's see how we're doing. I will ask you an easy question on one slide and the answer will be shown on the next slide. The best way to learn is to pause the video after each question and attempt to answer before moving on to the answer slide. Question number 1. What single logic gate will perform the same function as these two combined gates? Pause the video, sketch and name the gates shown, and then sketch and name the single equivalent before moving on and checking if your answer is the same as mine. This is an AND gate followed by a NOT gate, so a NOT AND function. The single equivalent would be the NAND gate. Try this one next, question number 2. This time, what single logic gate will perform the same function as the one shown here? Pause the video and make a sketch of the answer before moving on. Question 2 was a NAND gate with both inputs joined together. Therefore, whatever happens on input A always happens on input B. The inputs are tied together. So if the input is 1, the output is 0. If the input is 0, the output is 1. This is the equivalent of a NOT gate or inverter. And here is question number 3. What single logic gate will perform the same function as the two shown on the left? Again, pause the video and have a go at the answer. It's all good practice. The answer to question 3 is a buffer gate. This is a NAND gate with tied inputs, so it is acting as a NOT gate or inverter. The signal then passes through another NOT gate, so the output is the result of two NOT functions, and if we NOT a NOT, we have a null result, so we have no change in the signal between input and output. A 1 signal goes into the gates, is changed by the Nand to a 0, after which it goes to a second gate where it is inverted from a 0 back to a 1. 1 in, 1 out. A buffer and 0 in, 0 out is the same. Question 4 will really test you. Consult the truth tables for this one, or at least make your own truth table by putting 1s and 0s on the inputs and following the signal through each of the gates to the output at Q. Just one single logic gate will replace all those shown on the slide. Pause the video, sketch the circuit and decide on your answer before moving on. This logic circuit is equivalent to the exclusive OR function, the XOR logic gate. If and only if the A and B inputs are different to each other will there be a 1 on the output. If the inputs are the same, either 0, 0 or 1, 1, then the output at Q will be a 0. Understanding logic gates is an easily acquired skill. It just takes repetition and practice. In the later video, we will look in greater depth at logic gates and understanding some simple and not so simple circuits for those that are taking technical exams with logic circuits as one of the assessed components. And we will look at the interchangeability of the common logic gates, a trick that circuit designers will use if they have spare gates on other integrated circuits that will reduce the component numbers on the printed circuit board to gain a reduction in manufacturing costs. Thank you for watching. I hope that you found this video interesting and useful. Do let me know. Please subscribe to our channel to get easy access to all of our videos, and remember to click on notify to be sure of not missing our next video. And don't forget, you can also type in LearnElectrics into the YouTube search bar to go directly to our channel at any time from any computer or smart device. We're always adding new videos to our channel, so don't miss the next one. And once again, thank you for watching, and we hope to see you again very soon.